Hey everyone, and welcome to This Explainer. Today we're taking a deep dive into the very blueprint of modern artificial intelligence. We're really moving past the days of simple linear AI commands and stepping into this wildly dynamic world of multi-agent systems. Whether you're just sketching out your first digital worker or you're looking to scale an entire automated enterprise, the architecture we're talking about today is literally the difference between a brittle script and a highly robust autonomous system.
So what happens when AI stops just following rules and actually starts making its own decisions? To really wrap our heads around the magnitude of this shift, I want you to picture the difference between a train on a track and a rugged off-road vehicle. For the longest time, AI has been exactly like that train. Highly efficient, super fast, but strictly bound to the rails we laid down for it, right? But what happens when the AI leaves the tracks? What happens when it observes its environment, evaluates its goals, and dynamically plots its own course through totally unpredictable terrain? Well, that is the essence of autonomous agents. It's an incredibly powerful concept, but as any architect knows, going off-road requires a completely different kind of engineering. If you don't have the right sensors and safeguards, that off-road vehicle is going to get stuck in the mud, or worse, drive straight off a cliff.
To build this digital brain from the bottom up, we've got a clear architectural journey ahead of us. We'll hit on 5 main sections. First, workflows versus agentic AI. Second, designing agent memory. Third, reasoning and evaluation. Fourth, security and guardrails. And finally, number 5, the multi-agent enterprise. Let's jump in.
Section 1. Workflows versus agentic AI. This is the fundamental paradigm shift at the absolute core of advanced AI architecture today.
Every system architect faces a massive trade-off when designing a new solution. In a traditional workflow AI, you're following predefined deterministic steps. It gives you highly predictable execution and really strong governance. You know exactly what the system's going to do, every single time. But in an agentic AI model, the system dynamically decides what actions to take based on its overarching goals, its observations, and its own internal reasoning. It's super adaptable. But, and this is a big but, that adaptability comes at a significant cost. We're talking about a massive increase in both complexity and operational risk.
Because of that inherent risk, it is absolutely vital to cut through the hype and know exactly when not to use agents. Look, if you're routing an emergency 911 call, you definitely do not want an AI pondering its options, right? You want a rock-solid deterministic workflow. You should actively avoid agentic architectures if your process is simple, or if you're operating a heavily regulated process where predictable execution is literally a legal requirement. Plus, agents have to think, and thinking takes time and computing power. So if your system has strict latency constraints, where every millisecond matters, or you have strict cost constraints, traditional deterministic workflows are 100% the way to go.
Section 2. Designing agent memory. Let's say your use case actually does require that off-road flexibility. Well, for an off-road vehicle to navigate successfully, it needs a map of where it's been. For an agent to be truly autonomous, it has to remember.
Which brings us to a huge architectural hurdle. How do you actually implement agent memory at scale? It's not as simple as just saving a text file somewhere. A sophisticated agent requires different layers of recall, kind of like the human brain, so it can function efficiently without getting completely overwhelmed by processing its own history. If you get this wrong, your agent becomes sluggish, forgetful, and honestly, incredibly expensive to run.
Breaking down memory at scale actually requires 4 distinct layers. First up, short-term memory. This is usually held in session stores just to keep track of the current context of an interaction. Second is long-term memory, which utilizes vector databases. Think of these as databases that actually understand the underlying context and meaning of data for historical retrieval over time. But the real nuance? It lies in the difference between semantic and episodic memory. Semantic memory relies on knowledge bases. It stores facts, concepts, and knowledge completely independent of specific events. Episodic memory, on the flip side, uses event logs to store past experiences and specific interactions. So knowing what a client is, that's semantic. Remembering that the client was really angry on a call yesterday, that's episodic. You absolutely need both for a truly smart agent.
Moving right along to Section 3, reasoning and evaluation. Once our agent can remember, we actually have to teach it how to think.
A cornerstone of advanced reasoning is a concept called reflection, spelled with an X. Reflection is a process that allows agents to critique their previous actions in order to improve their future behavior. Imagine a coding agent that writes a buggy script, analyzes the error logs, and then fundamentally changes how it approaches Python syntax for tomorrow's tasks. This is all about long-term systemic behavioral improvement.
Now contrast that with self-reflection. This is a process that enables iterative self-correction before finalizing and delivering an output. Basically, this is the agent double-checking its own work in real time. Think of it like the agent drafting an email, realizing, yikes, this tone is way too harsh, and rewriting it internally before ever hitting send and showing the user the final result.
So, the crucial takeaway here is understanding the completely different time horizons these two frameworks operate on. Reflection looks backward at past actions to upgrade future intelligence. Self-reflection looks at the immediate present, fixing outputs iteratively before they're finalized. An enterprise-grade agent? It usually utilizes both of these to continuously optimize its logic.
But how do you actually measure if this reasoning is working? Well, architects must rigorously evaluate agent planning quality. When you're benchmarking different reasoning frameworks, like, say, the popular React model versus a plan and execute model, you have to measure very specific metrics. You compare task completion rates, obviously, but also latency, how efficiently the agent uses its given tools, the qualitative reasoning quality, and the overall cost across benchmark tasks. If you choose the wrong framework here, you don't just get bad answers. You get sluggish, incredibly expensive systems that frustrate your users and just burn through compute.
Section 4, Security and Guardrails. Okay, so we've built an autonomous, thinking, remembering, off-road vehicle. But what happens when that vehicle suddenly guns it for a cliff?
One of the most common and dangerous cliffs is the infinite loop. Literally nothing burns through your cloud computing budget faster than an AI vigorously agreeing with itself in a flawed, endless loop. An agent can so easily get stuck executing broken logic over and over again. To prevent this, strict fail-safes are an absolute must. Architects have to set maximum iterations, enforce hard cost limits, and set strict timeout thresholds. On top of that, you must actively validate the agent's progress and implement loop detection mechanisms so the system can actually recognize when it's just spinning its wheels and automatically pull the plug.
Another absolute lifesaver of a guardrail is the human in the loop. Human oversight cannot be an afterthought, guys. It must be procedurally designed right into the architecture from day one. What does that mean? It means implementing approval checkpoints right before any high-risk actions, like executing a massive financial transaction. It means designing escalation paths for whenever the agent makes a low-confidence decision. And it requires comprehensive review workflows, especially if you're operating in regulated domains like healthcare diagnostics or commercial loan approvals. The agent does the heavy lifting, sure, but the human holds the keys.
We also have to secure the tools our agents use to interact with the world, while simultaneously preventing prompt injection attacks. That's where malicious users trick the AI into ignoring its core rules to do something it really shouldn't. This requires a rock-solid defensive architecture. You need to apply role-based access control, or RBAC, and strictly enforce least privilege permissions. You use tool allow lists so the agent can only access explicitly approved functions. And to stop that malicious prompt injection, you have to meticulously validate inputs, isolate retrieved content, implement strict context boundaries, and constantly verify the outputs of the tools themselves.
Section 5. The Multi-Agent Enterprise. Now that we have a secure, intelligent, and highly capable single agent, how in the world do we scale this?
The real secret to scaling is realizing that one agent shouldn't do everything. Instead, you build a digital workforce. And hey, a workforce needs a manager, right? Enter the supervisor agent. You can compare the supervisor agent to a traditional project manager who delegates tasks and tracks milestones. It's a specialized agent designed specifically to coordinate other agents. It assigns tasks, monitors their execution, and then consolidates the final results from its team of digital workers into one single cohesive output.
Working really closely with the supervisor is the router agent. Think of this one as the intelligent dispatcher. The router agent analyzes an incoming request and determines exactly which specialized agent or which deterministic workflow is best suited to handle it. It ensures that complex, ambiguous logic tasks go to heavy reasoning agents, while simple data retrieval goes to traditional, low-cost deterministic workflows.
When orchestrating these complex multi-agent systems, architects often look at frameworks like LangGraph and CrewAI. These actually represent fundamentally different philosophical approaches. LangGraph focuses heavily on graph-based stateful workflows and orchestration. You choose LangGraph for highly structured step-by-step state management where rigid compliance is absolutely key. CrewAI, on the other hand, emphasizes role-based multi-agent collaboration. It treats specialized agents almost like human employees with specific job titles collaborating on a project. You choose CrewAI for creative problem-solving and highly dynamic research tasks.
To support these frameworks at an enterprise scale, you really need to conceptualize your platform in distinct groups.
First, you need traffic control. That's your AI gateway and your agent registry to manage incoming requests and keep track of your digital workforce. Next up, you need cognitive infrastructure, the planner layer, a shared memory layer, and a secure tool layer. And wrapping the whole shebang up, you must have an ironclad layer of security, observability, governance, and multi-tenant isolation. Let me tell you, this requires robust communication protocols like event buses and standardized schemas just to keep all these moving parts perfectly synchronized.
To truly visualize this in action, let's consider a principal architect scenario. Imagine designing a unified multi-agent enterprise platform where finance, HR, legal, and customer support all operate within one shared infrastructure. Let's say a customer emails about a broken product. The customer support agent reads it, routes the complex refund request to the specialized finance agent, pings the HR agent to notify the assigned account manager, and logs all the compliance steps with the legal agent, literally all in a fraction of a second. They utilize a shared memory layer, common security protocols, and unified governance, all overseen by human-in-the-loop approvals. This right here is the ultimate picture of the multi-agent enterprise.
We have covered a tremendous amount of ground today, from the fundamental shift away from deterministic workflows through memory and reasoning, all the way to enterprise-scale security and orchestration. So I'm going to leave you with this final critical thought. As we transition from AI that merely assists to AI that actually operates, the question is no longer if you will build a digital workforce, but whether you will be the architect of it or be replaced by it. Thank you so much for joining me on this explainer, and I really hope this blueprint helps you build smarter, safer, and incredibly capable systems.